All right, here we go. So we have exam on Monday. Is that right? Okay. Exam on Monday. Now, on the exam, there are questions about the Unix command line. So we must keep using that and practicing that. And I'll work. I just want to show you me working for a moment, just to, so you see a little bit more of this. Clear is a command. I'm going to use that just to clear the console window. And I wanted to save the work that we did last time. We don't need to see the .o. That means it's an object file. That's a temporary file, an intermediate file in the compilation process. Sometimes they get created, and they're normally created and then deleted, the way we've been compiling the code. But sometimes that might not happen for whatever reason. And so I'm going to remove this file right there. So it's rm main.cpp.o. So that's gone. I use ls to see what's still in there. So I have 4 files that are visible to me. Notice the point.c9 is not visible because the dot in front of the file name is a part of the file name, to start the file name. That's a suggestion to whatever tool is accessing the file system to not display that item to the user. But so ls won't show that. But if we do ls minus a for all, then it'll show us the .c9 hidden folder. So we call this a hidden folder. Windows has a version of this as well. They use a different approach to it. It's not part of the file name. It's part of a property that's attached to the file. So I'm going to I can remove a.out. We don't need that. See, I can use ls to see what's going on, but obviously it's also visible from here. So I want to work in main to do other problems today, but I want to save what we have. So I'm going to copy main.cpp to, I'll call it point main. That's the main for the point example, the point class. We looked at that last time. And let's say I want to simplify my folder here. So I'll create a directory, mkdir, and I'll call it point. And you can see it from ls, you can see it in the visual display up there. And I want to move those files into it. So I could go point, and I notice both point.cpp and point.h, both of those files I want to move. So I can use what's called a wildcard, which is an asterisk. And that matches against anything that follows the point. So it'll match against H, it'll match against CPP. They'll move that into the point folder.
So we have to have the point and then the asterisk after it?
Say it again?
We have to have the points, like the period and then the asterisk?
What do you have to have it? What do you mean have to? Huh?
Well, in order to move multiple files into another
Yeah.
location,
Well, you can.
period and then the asterisk.
Yeah, that's right. So I just moved them into the folder. But look inside the point folder. There's the 2 files. Yeah.
What does the mv point dot asterisk point do?
Oh, this move.
Yeah, move point to point.
Yeah. Well, this point was the folder.
Okay.
See, here.
Yeah.
So when I moved them from the current directory, this matches the 2 files that were in my current directory, and I moved them to the destination directory.
Okay. But what is a dot and then?
Well, dot, see the files have a dot in them. See point.cpp,
Okay.
point.h. The asterisk is what's called a wildcard.
Okay.
You know, like in poker, it's the joker. You could use that for any card. So we say that it, you know, so so this symbolism here represents more than one file. It represents, this is like a template, like a pattern. And it's saying, take all files that fit this pattern. And the pattern is, the file name has to be POINT dot followed by 0 or more characters. So this asterisk just says anything can go there. Any number of characters, even 0 characters. So it matches against that point H, you know, I mean the H, and it matches against the CPP.
So as long as the file has the word point with a capital letter, does that matter?
The capital letter is important because it's case sensitive. If we had done, watch this, if we tried to remove point.h, this is going to fail. I hope it fails. Yeah, I'm sure it's going to fail. I'm sure it's going to fail. Whew. Right. And sometimes on the Mac, because I'm on a Mac now, but the file system we're working on is Ubuntu, right? It's Linux. Sometimes on the Mac will be like Windows, and it'll be case insensitive when you're working with file names. I noticed that. And so it's a little fuzzy on the Mac how they do that. You have a question?
Do we need to have slash between point and point dot h? Or
Yeah, you have to have a slash.
Okay.
Because if we just said point.h, where the assumption is that it's in the current folder, but it's not. You know, we're at this level here,
Okay.
but the point.h is inside the subfolder relative to where we are. So this is different than here. We have to give the name of the subfolder, and that's called a path name. You understand the word path? Path name. It shows the path, the trail, how to get there. You know, like maybe we're going to go up, and then we're going to come down, and then we go into point, and then we go into point.h. Like, that's a path. It shows the steps that you need to step on to get to some destination. So it's, we say path name, a name that contains a path within it. Now I also want to move, you know, if you look here, point main, I need to move point main into the subfolder. Now, that might make you feel more comfortable. You put a slash there just to make it look like it's a folder. But actually, you can do it like this. Did you see it pop in there? So now we have just main and the subfolder point. So we got those files out of the way. So you need to practice these to get good at this and to do well on the exam. Especially the thing about, like if we're down in here, let's go into the point folder. I'm going to CD into the point folder. You see a PWD shows me where I am. And I can see the files in there. And it's like, oh, maybe I want to look at, you know, the main folder, the main.cpp file. So if I do ls ... I'm saying, give me the listing of my parent. Show me the contents of the folder that contains the folder I'm in. That's called my parent folder. So there's the main. So we could use maybe nano, right? We can use nano to open that up. So I got to go // main.cpp. So once again, there's the path name. .. means go up to the parent / and then within the parent folder, grab the file main.cpp. And I don't use nano, but that's how you do it. what if on the exam it says copy of file. Maybe I'm going to make another directory. I'll call it temp. Look at that. See? Look at this. And I'm going to cd into temp. So now we're getting deeper in the hierarchy. So let's suppose the exam says, all right, there's a file named main.cpp in the home folder. Okay. Show the command to make a copy of that file into your current folder. And make no assumptions about the location of your current folder. So the command you give should work from any location. Once again, make a copy of main.cpp, which exists in your home folder. Make a copy of that file and have the copy placed in your current folder, wherever that happens to be. So we do copy cp tilde for home folder slash main.cpp. Oh, you know what? It's not in the home folder. It's in the workspace folder. Sorry, it's in the workspace folder. So that's so if main.cpp were in the workspace folder, which is a folder in the home folder, then this is the path name to get there. And the destination is just dot. That's my current folder. If I want to rename it, then I would just give it, a new name, like hi.cpp. I could use that. And that, by the way, that'll put it into the current folder. So that's not needed. Just the name itself is good enough. See, so hi got in here. But hi is just a copy of main.cpp. The contents are the same. The names are different. The locations are different, obviously. So practice these. I got to tell you, this stuff turns out to be very useful, highly useful, extremely useful. So depending on what you're doing, obviously. But if you're doing software development, and especially web development, anything to do with networking, like mobile apps, things like that, this is really important to know how to work at the command line. All right. I emptied out this temp folder. I cd up to the parent, then I'm going to remove it. Just cleaning up. I'll cd up into the workspace. That's where we are. It's good enough. So last time we talked about classes. And there's only one more topic in the course, which is application development. One more topic. Of course, this is a gigantic topic. And exam 2 is coming up. Here's some sample problems, but look at all of the, the previous assignments. They all contain material that could appear on the exam. So what do we want to do today? I just did a little bit of review about the command line. And we can go over classes again, or we can start application development, or I can answer questions about problems that may appear on the exam on Monday.
Probably exam.
Can you do one of the exam 2 problems?
Do an exam 2 problem?
Yeah, the one with the array.
One with an array?
It's number 3.
You mean a vector or array?
Number 3.
Number 3.
This one here? Oh yeah, that's an array. Count the negatives. How many negative numbers are in an array A that gets passed into a function? Now the dimensions are given, 100 by 100. So on the exam, it'll look like this. We're not going to look at that. Oops, I didn't want to do that. So, you know, on your exam paper, just to show you, like, you're not going to be, it'll be like problem 3, and then you'll have the problem statement here, right? And then there'll be, you know, this will be given. This will be given. And, you know, implement the following. So the exam will look like there'll be more instructions, you know, describing what the function does. So your job is to implement this. So you don't need to, you know, put main or include or using namespace. You don't need that stuff. I just want to see that the statements that go into the function. You don't have to rewrite this either. It's right there on the exam. You don't have to rewrite that either. Just show me the statements that comprise the function. So I'm going to show that to you, what that'll look like. So you're going to count the negative numbers in an array, and it's an array that's 100 rows and 100 columns. And so what is that? That's 10,000, right? 10,000 items. So out of 10,000 numbers, how many are negative? We have to look at each item. And to look at each item, we'll use loops. We can't check, you know, each one individually. We can't say if a of 0, 0 is less than 0, that's negative, right? Then increment the count. And then if a of 0, 1 is less than 0, then increment the count. We're not going to do it. We can't do it like this because we'd have to write 10,000 lines. We'd have to have 10,000 lines of code here for this to work. So we have to use loops. So what we're going to do is something like this. Whoops, sorry about that. Instead of having hard-coded indices in here, we'll have to have, you know, rows and columns. And we're going to have some loops here. So we have to let, you know, for r equal to 0 to 99. And then for columns starting at 0 to 99 as well. And we start with a count equaling 0. And then once we're done this, we'll return the count. So there it is in pseudocode. Pseudocode means like a fake code, you know, something that's close to code, but it's not code that'll compile. And I'd be pretty happy if you showed that to me. I'd probably give you full credit for that. But you'd have to get if you did this, you wouldn't get full credit anymore. So I don't recommend using pseudocode. I recommend using C++ code, but if you want to, you can start with it like this, and then try to move it into C++ code. So let's see, we just do this for int r equals 0, r is less than 100, plus r. For int c equals 0, c is less than 100, plus c. And then inside this loop, we just check A of R, A at RC, is it less than 0? If it is, increment the count. And then when we're done, we return count. We'll need a semicolon there. There's the code. You see, what this code does is the outer loop is like the hour hand on the clock, and the inner loop is like the minute hand. So for the hour hand to advance 1 hour, the minute hand has to go all the way around. See? So for R to advance by 1, C has to go from 0 to 100 and back to 0 again. Then R can go forward by 1. Yeah.
What are those 3 statements which started with the if?
This? This is if you wanted to do it manually. You'll need 10,000 lines of code.
Oh, okay.
So we can't do it. But I wanted to show you how this is actually what the loop is doing. See, we start with R equals 0. See, that's this 0 right there. And then for R equals 0, we start C at 0, and then we increment C on the inner loop. So that the C, see, R is 0 all the way. R is 0, C is 0. R is 0, C is 1. R is 0, C is 2. So R is, right now, it seems like R is fixed at 0 because it's in the slow outer loop. It's the C that's rapidly changing, right? So C has to, we're going to continue that process in the inner loop until we get to the last operation, which is A099. Now, when C hits 100, we don't do this. When C hits 100, the loop condition, when C hits 100, the loop condition is false. So when C hits 100, we do not do this if statement here. That's why I didn't show it. A099 less than 0, that's the last time for this run through of C. That's the last statement that runs. That's the last version of the statement that runs. And C is 99. And then the very next line is if A of 1. And then what goes in here? 0. Yeah, good. Good job on that one. So we're starting all over again. And then it's A10, and then we go A11 and A12 and so on. And we do that all the way up until we hit A199. And then the second pass through the inner loop has completed. And then we go on to the next one. Which is A20, A21, A22, and so on. So that's how the loop is, that's how this loop is running. It's called a nested loop. There's one loop inside of another loop. When you have a nested loop, you get a lot of calculations because it's like a multiplication. So it's 100 passes through the outer loop, 100 passes through the inner loop. That's 10,000 total operations that are performed at the deepest part of the nesting. So that's a lot more operations that if you have like one loop that finishes, and then following that loop, you have another loop. Those are like loops that are done in sequence, are nothing. They're very, very cheap instead of the costly nested loop. because when they're done in sequence, it's the time required is the result of adding, is the number of times the first loop runs plus the number of times the second loop runs. But when you have nesting, it's the number of times the outer loop runs times the number of times the inner loop runs. Is that good enough?
Yeah, I just had a question.
So this will be your answer. It'll look just like that. And what's your question?
Shouldn't the return count be between lines 11 and 12?
Should the return count be what?
Between lines 11 and 12? Because right now it's out of the brackets.
So like that, right?
Yeah.
So we're only gonna we're gonna set R to 0, run C from 0 to 100, and then return. We never get to R equal 1. See, R never gets a chance to get to 1 because we exit the loop with the return statement. We only get one pass through the inner loop. Does that make sense? This is a common mistake. It's a very good question because, and I appreciate the question a lot, because that is such a common mistake on the exam. That people are returning inside the loop when you're supposed to be returning after you complete all the looping. You don't have to write using namespace stdin and none of that stuff. Just that right there is good enough. Any other questions? Yeah.
Number 2.
Number 2. Let's look at that. Min value. Let's do this one. So we have a vector v. What's the smallest value in v? Return that. See, the function returns an int. And that int represents the smallest integer that's in v. Return the smallest integer that's in v. We'll just use this template right here. Number 2, implement the following. Min value. So we need to know the smallest value in v. So we know we're going to have a loop there. And it's going to go up to v dot size. So we got to find the smallest value, we got to look at every value in there, in the vector. So the way to look at a value in the vector is to use an index. So that's why we need the loop. So we're going to look at v of I. See, we're going to look at v of I. So we're going to look at v of 0, then we're going to look at v of 1, then we're going to look at v of 2, all the way up to v of size minus 1. And then when I hits v dot size, then we exit the loop, we're done. And then we're going to return the smallest value. Oh, there, so we got to have a variable there, smallest. We're going to need that. And the trick here is how to initialize that. And then for each v, you want to check, you say v, if v of I is less than smallest, then we found a new smallest. If v of I is smaller than smallest, we found a new smallest. And then when we finish the loop, we pulled out the smallest value. We've looked at every value. Whenever we found a new smaller value, we changed the state of this smallest variable. All right, now I'm going to show you how to do it wrong.
Is it wrong?
Yeah, there we go. I just did it wrong. I was just seeing if you were awake. You are. So we're going to set smallest to 0. Now, why is that a problem?
Is it the value of 0?
Huh?
It gives it a value of 0 and not index 0?
No, that's not it. Why is this a logic error?
Because we initialize the smallest equals to 0.
We initialize smallest to 0, yeah. So why is that a problem?
The smallest in the vector might be greater than 0.
The smallest in the vector might be greater than 0? Greater than 0?
Less than.
Less than 0. The smallest value in the vector could be less than 0.
Yeah.
So we never find anything that's less than, that's bigger than, that's less, so we never find anything that is less than, is that right? Wait a minute, did I say that wrong? I said it wrong. The problem is, oh, I'm sorry. You said it right the first time. If all the values in V are larger than 0, then this won't work, right? I was thinking about max value. That's what I was thinking. Sorry to mess you up on that. So let's look at a counterexample here. So if V is 2 and 5, this algorithm here would produce 0 as the smallest value in V. See, this is the problem we have with max value. Remember, max value is if you had all negative numbers in V. Now, if we had this for V, then this algorithm is okay, because a 5 will be smaller than 0. 5 will be smaller than 0. I mean, minus 5 is smaller than 0. So what's the problem? How do we fix this? We initialize smallest to what? Does everyone know this, or is this obvious? Is this obvious? Huh?
Isn't it V brackets 0?
Yeah, V0. Is that obvious? I wasn't sure. We have to set it to something. If we set it to something in V, then we know we're not going to have the problem of initializing it to something that's smaller than everything in V, because we set it to something in V, at least one thing in V. We could have set it to, V dot size minus 1. We could set it to that. Oh, wait a minute, I'm messing that up. That's the last item in V. We could set it to that. That would be okay too. We could set it to V of 2, assuming that there's 3 values in V. That's the problem with setting it to V of 2 or anything else is, well, V has to be big enough. What if V only has 1 value in it? Well, if it only has 1 value in it, then that'll work. Now, if V has 0 values, then what's the minimum value of an empty vector? It's a meaningless question, right? So, I mean, in code, you might have an assertion, that V dot size is greater than 0. Because if it wasn't, then the whole concept of a smallest value is meaningless if there's no values to look at. But we don't need that for the test. So that's how you do this one. Sorry about that moment of confusion there. Anything else? Do you want to look at them all? Is that what you want to do, or just run through them? You want to see R identical? Yeah, that one? Okay. R identical. Let's look at that one. Yeah, and these are great to practice. I just want to do the application development topic. That's what I want to do. Okay, but I'll do this, I'll do this because you're the boss, not me. All right, so we got to see if A and B, well, first of all, we're not given the length. What if the length of A and B are different? Then they can't be identical. So we got to check to make sure that A dot size, check that if it happens to not equal B dot size, then we're going to return false. They can't be identical. They have different numbers of values. And we'll just take care of that issue from the beginning. Now we don't have to think about that. Now what we got to do is look at each item, you know, a, you know, we want to test this. We want to see that does A0 equal, you know, B0? And does, you know, this is the check, right? Is that true? And we want to see that, you know, is A1 equal to B1? A2 equal to B2, and so on. For as many values as we have. Now, on purpose, I'm going down the wrong path. I am going down the wrong path on purpose. Anybody know what I'm talking about here? It's like if A of 0 is B of 0, what do we do? We can't do anything. We got to go ahead and check the next one, right? And if A of 1 equals B of 1, what do we do? Well, the only thing we can do is look at the next one, because we have to look at all of them. And then after looking at all of them, if they're all good, then we'll return true, they're identical. Now, when do we return false? They're not identical. You see that how the problem, how you have to structure this? We know we're going to be going through the whole vector, so let's just take care of that code right here, and then we can forget about this part. There's a block of code. That's a loop that lets I range across all the valid indices for V, for A and B rather. But that's V, that should be A. A or B, they have the same size, so we can use A. So what are we doing here? Do we do this? Is that what we do? What could we do here? I don't see we can do anything there. We can't make any conclusions about what we're going to return right there. Because we're looking at one pair, whatever I is, maybe I is 3. What can we conclude when A of 3 equals B of 3? Huh? Yeah, at that index, those two values are identical, but it's not going to help us in deciding at this moment. What do you suggest to do? I'm sure there's a bunch of you that know the problem here. I'm going slow on this point because many of you, this hasn't clicked yet, how to structure this, how to get this written. Yeah, over there. So we basically, this is useless to us. We want to look at this. That's what we want to know. Because if we found a pair that doesn't match, hey, they're not identical. We'll return false right there. Does that make sense? All right. Trying to nail that in. I don't know if it's sunk into any person today or not, but that's, and then when we're done the loop, then we know they're identical because we never found a pair that didn't match. And that's how you do that. And that's a common issue in so many of the problems is knowing what to test here inside the loop. All right, that's that one. Any questions on that one? Yeah. This first, in this one here? No, look, the A dot size and B dot size will never change. We're just checking to see if A and B have the same size. Otherwise, the loop is not meaningful. The loop will not be meaningful, so we keep that outside the loop. You see that? No, we could do it like that. You're right. We could do that. We could require that that they're the same size. We could do that, but that's not. I guess it's the problem statement. If we wanted to do it like this, we'll just now assert will terminate the program if it's false. So is that the behavior that our client, our boss, or ourselves wants to have? Do we want to terminate the program when A and B have different sizes? Or do we simply want to tell the calling code that they're not identical? So that depends on the purpose that you're using this code for, and we don't know what that purpose is. So both of these answers would be okay for me on the exam. Any other questions? Okay. Yeah, if I saw you did that, that'd be fantastic. I mean, that'd be great. I mean, it's obviously you're locking into the answer. Yeah.
Or we can switch the statement also, right? Like if we say if A I equals to B I, return the false, otherwise return the true. I mean return the true and otherwise return the false.
I really appreciate you bringing this up. So we'll never hit here.
Okay.
Look at this. If A of I, let's suppose we enter into the loop, all right? We enter the loop, I is 0, and then we come here, and we compare A of 0 to B of 0. And let's suppose they're the same thing. Let's suppose that A of 0 equals B of 0. What do? We return true, they're identical. But what about A of 1 and B of 1? We didn't look at those, did we? But we're returning true by only looking at one pair. You see the problem? You get that? We need to look at all the pairs. We can't return true until we look at all the pairs. Yeah.
So that would just end it after the first one, right?
Yeah, this would turn exactly.
Once it sees it, it won't check the rest. Right?
Won't check the rest. Thank you for suggesting this. This is so common. I got to see. This is a very common solution that the students present. But think about this carefully. This does not solve the problem. Yeah.
How about if we just return false at end of, once we're done with the for loop, like just the bottom, we can eliminate the else statement. Are we able to do that?
All right, well, let's suppose that A is 9, 2, and B is 9, 4. Are these two vectors identical?
No.
They're not identical. They are not identical. But you're going to compare A of 0 with B of 0. Is A of 0 equal to B of 0? Yeah. So that means you'll end up returning true because you didn't look at A of 1 and compare it to B of 1. It's like a puzzle. It's like playing Portal 2. Does anyone play Portal 2? How many people play Portal 2? I'm just curious. One person played Portal 2? Wow. Or Portal 1, for that matter. It's a video game full of logic puzzles. This is just a logic puzzle. Okay, so what I'm hinting at here is this. You can experience this material as if you were playing a video game. That's the subtext that I'm trying to get at. Okay, so what Is that enough on this one? Or any more questions? No, okay. What about search? Linear search. Do you want to do this? Because we did this before. I can do it again. Yes, okay. All right, so linear search. Find K and V. There's a vector V that's being passed into the function. The function name is search. That makes sense. It means look for something. Look for what? Look for K. K is an integer. Look for K and see if you find it inside of this sequence of integers called V. If you find it, return its position. Like if it's in if it's in slot 0, return 0. If it's in slot 1, return 1. And if you don't find it, what are you going to do? What's the convention? If you don't find something, you don't find a value in an array, how do you let the calling code know you didn't find it? You return a what? No, it's an int, returning an integer. Not 0. 0 is the first position in the array. What was that? -1. And -1 is not a valid position in a sequence. The sequence starts at 0 and goes up to whatever. So we, by convention, we return -1 to indicate that the value you asked me to look for isn't there. All right, let's do this. So we have to look for this. So we know we're going to have to scan through the vector. So we'll use a for loop. Look at that standard loop right there. So if we find it at I, what do we do? Can we make a conclusion? Or do we have to wait and look through the whole vector? Huh? Do we have to look, if we found it at I, maybe I is, say, 3. We found the number K in position 3. Can we make a conclusion here? Or do we have to keep looking? Huh? What do you think back there? Huh? Yeah, return that position. Thank you. Good job. You found it. Why keep looking? Want to look for another one? So, but what about if we don't find it? What are we going to do?
Keep looking.
Huh?
Keep looking.
Well, you can't. We keep looking. I go into an infinite loop. It's like the program has crashed. Go into the control panel or something and kill the process. Okay. So what do we do if we don't find it?
Return the false or return the 0.
Huh?
Return the 0.
Return 0? It's in that. If we return a 0, we're saying it's in position 0. -1. Where do we return -1? We do it like this. Sorry about that. Messed that up. How's that look? Not good. Does that look bad?
Yes. We had to return -1 at the end of the for loop.
Yeah, and we have to return -1 at the end of the loop because This is the same problem we looked at last time. We're only going to look at position 0. Well, we don't want to just look at position 0. If we find it, we got it, great. We'll celebrate and return. But if we didn't find it at I, well, we got to keep working. We're going to look at the next I. All right. I know I'm probably going over this too slowly for some of you, and others I'm going over it too quickly still. I know. All right, so what do you want to do now? We did all the problems here. Oh, we didn't do binary search. Do you want to do that one again? Just run through it again, just to help you memorize it, because it's just a memorization problem, right? It doesn't have to be a memorization problem. You could actually derive it during the test, but that's hard to do. Let's change the name to binary search. And here, we're operating under the assumption that the numbers in V are increasing. And this algorithm assumes that. It won't work unless that's the case. But we can't, there's no simple assertion to use for that. So here, what we do with binary search, we have this vector, we have to slice it in the middle. So we have a loop, and it's some kind of a while loop with a condition here. And we need to slice this vector in the middle. Well, basically, I'm going to just do it quickly. We start with a start position and an end position. So we have a start position and an end position. So like if we had this vector here, yeah, do it like that. Maybe the vector looks like that. So we want the start position here and the end position here. So that's a range. And we're going to start with say it's somewhere between S and E, including the endpoints S and E. We didn't look at any number yet. So it's going to be in there somewhere. And so what we do is we want to look at the middle item that's in the middle of those two. So we use the midpoint formula, which is just the average of the start and end indices. So that means M will calculate out to, somewhere in here, whatever it is. So we calculate M, and then we're going to look at M. So if V of M, I like to do it like this. We're looking for K. If K is less than V of M, then we know, if K is less than 15, then we know that K, if it's in there at all, it's in this range that I've highlighted. Because if K is less than V of M, which is 15, that means the position of K must be less than M. It could be at S. It could be at M minus 1. It can't be at M, because we looked at M. And it can't be bigger than M, because the numbers are in increasing order. So if K is less than V of M, good. We're going to reset our endpoint to M minus 1. You're going to shrink the range. We could cut out the top half. We do that by bringing e down to where m is, just in front of m. We don't have to bring e to, we don't bring e to m itself because it's not at m. So that's why we can do that -1, see, and put it there, because we know that k is not at m. And let's do the other one. Else if, what about the other way? If k is greater than v of m. If k is greater than v of m, that means k is going to be in that range. In that case, we're going to discard that part by taking s and moving s up to that position, which is m plus 1. We don't have to put, once again, we don't put s at m directly because k is not is bigger than m. So the smallest, the nearest position that we could find it at, the lowest position we could find it at is m plus 1. If it's there, it could be there. We can't rule it out yet. So we're going to bring s up. S is going to be m plus 1. Else what? If k is not smaller than v of m, and k is not bigger than v of m, k equals v of m. We found it. So we return m. Remember, we need to return the position of k and v. We found k at m. M is the position of k and v. That's why we return m. Now this loop is gonna, we might not find it. So we gotta see, s is getting bigger, m is, and e is getting smaller. And at some point, they're gonna cross each other. And that's when we stop. So while s is less than or equal to e, because if s and e are equal, we want to do the comparison. If s and e are equal, then the average of s and e will be either s or, s and e. If s and e turn out to be 9, based on our calculations, if we put s and e at 9 at some point in the algorithm, then the midpoint will be calculated like there, right? That's the, when we average s and e, we're just going to get whatever value they equal. And then we need to look at k of m. So we want to, that's why I have the equal sign in there. It's okay, do the loop if s and e equal each other. Well, think what happens. Let's suppose that k is 10. So it's not 9. It's not in there. If k is 10, that means k is bigger than v of 9. I'm sorry, v of 2. It's bigger than v of m. So that means we increase s by 1. So now s gets pushed to here. Now this doesn't make sense anymore. S is bigger than e. So we're done. So then this loop condition is now false, and we exit the loop. And when we exit the loop, we know that we didn't find it. So we return -1. That's not a bad little algorithm right there. Is that useful to you to go through that again? You got to go through that on your own now, right? Try to do the reasoning. And because if you go on in this field, you'll need to deal with more complicated algorithms. And this is like the beginning of that, those complicated algorithms. Binary search. This is the first non-linear thing that we've done in the class. And then sorting is, would that be non-linear? Yes, I don't know. So what else do we want to do here? Is that enough? That's enough for today. We went through all the problems. Make sure that you can still do the earlier problems. I think I may have included these type of problems in there again. I think so, I'm not sure. But these should be easy for you now, right? These will appear on the final. So if you study for these for the midterm, it's not going to be a waste of time because they're definitely going to be on the final, right? I think I put some of these on the midterm, but I'm not sure. And this integer division, floating point division, generating random numbers, you have to know how to do that, right? You use rand. So you need this. That generates a random number. Now, if you want a random number that's less than 100, you have to do mod 100. If you want a random number in an interval, suppose you have the interval 20 to 50. Well, you look at the range. The range is 30. So you need a random number between 0 and 30, and then you just take the start point and add that to it. This will go, actually, this is not correct, is it? Because this, the way we've written it, that'll generate numbers that, so rand could be 0, and rand mod 30, what's the largest value that rand mod 30 could be? Huh? 29. Because it's a remainder. So if you divide by 30, the biggest remainder you're ever going to get is 29. You're never going to get 30 as a remainder because you take another 30 out. All right, so that's 0 to, that's 20 to 20 plus 29, right? That's 49. So we're in this range here. So it's not quite this, right? If I did this, like in math notation, that means exclude the endpoint. So that'll be okay. But if I give it like that, then, well, we need 30 to be the largest value we get. So we got to use 31 there. And that'll produce values that are in this range. Because that means the biggest value we can get here is 30. So 20 plus 30 gives us 50 as our largest number. So that's how to do that one. And is prime, you got to know how to do this. I don't know, I may have put that on the test, right? Is prime, implement is prime. Remember how to do that? In n is prime, if you try to divide n, if you do n mod I, there are a whole bunch of i's, and you never get a 0. If you get a 0, if you go n mod I in a loop, and you get a 0, then you return false, it's not prime, because I found a divisor. But if you finish the loop and you don't return false, it's not prime, then it must be prime. Then you return true. So that's how you do that. Huh? I what?
Begins at 2.
I must begin at 2. But don't begin at 1. And don't begin at 0. Yeah, so you have to begin at 2. That's right. Use all zeros, you should be able to do that, right? You have a counter, and you increment the counter by 1 when you find a 0. Same with count occurrences, same thing, you have a counter. You increment the counter every time you find K in A. This is R identical. You don't have to test the length being equal because you just only have one length there. This, some form of this is on the midterm, I remember. I think it was like is lucky. Maybe I changed it to is lucky. Or I kept it at is unlucky. But I changed the definition, so there's another way to decide if it's lucky or unlucky. So you have to be able to handle a new definition of what lucky or unlucky means. So make sure that you can experiment with that, try different things. I think that's enough, right?